During the pandemic, our world turned upside down, right? We all stayed home, we watched the numbers, and we really hoped the big policy decisions were the right ones. But here's the tough question. How do we know if those policies really worked? I mean, for sure. Or was something else, a kind of phantom in the machine, fooling our data the entire time?
So here's our game plan for this deep dive. We're going to start with that high-stakes question, then uncover a really weird statistical puzzle called the null paradox. After that, we'll unmask the phantom culprit, see how a new tool corrects for it, and then put it all to the test with real-world pandemic data. Finally, we'll talk about why this matters so much. You have to imagine being a scientist or policymaker in the middle of a crisis. The pressure is just immense. Every decision is life or death, and it all comes down to the data. But the single biggest challenge is figuring out if two things happening at the same time is just a coincidence or if one is actually causing the other. And that brings us to the core question. We all saw the charts, right? As our mobility dropped, the number of deaths in many places also went down. That's a correlation, plain and simple. But did one cause the other? Answering that, well, that's a whole lot harder than it looks.
To even try to find an answer, scientists use these incredibly powerful tools called augmented epidemic models. Their job isn't just to track what's happening. They're built to answer the big what-if questions, to look into an alternate reality where we didn't lock down, to see what would have happened.
And this is exactly where our mystery begins. Because sometimes the very tools that are supposed to give us answers can get things completely wrong. They can fall victim to a problem that's so sneaky, it's actually called a paradox.
Say hello to the null paradox. Okay, get this. It's a situation where a totally standard, trusted model will tell you with absolute confidence, hey, this policy had a huge effect, when, in reality, the true effect was zero. Nothing. It's like the model is seeing a ghost.
So picture this. You run your data through a standard method, something with a fancy name like maximum likelihood estimation, or MLE for short. The model chews on the numbers and spits out a clear result. There's a strong link between your policy and the good outcome you wanted. Looks great, right?
Well, here's the twist. The null paradox tells us that strong connection could be nothing more than a statistical mirage, an illusion created by something hiding in the data. And, if our leaders are making huge decisions based on an illusion, the consequences could be absolutely massive.
So if the effect we're seeing is just an illusion, there's got to be a magician, right? Let's go ahead and pull back the curtain and see what's really going on here.
The source of all this trouble is something that researchers have appropriately named a phantom. It's a variable that we can't see, we can't measure, and it's just lurking in the background of our data, quietly messing up our results without us even knowing it's there. Now, this is a really important distinction. You might have heard about confounders before. Those are hidden variables that affect both the policy and the outcome. But a phantom is way sneakier. It only affects the outcome directly, but it creates this false phantom link back to the policy through a weird kind of statistical ricochet. That makes it so much harder to find. Basically, this phantom creates a secret backdoor path in the statistics. It's a ghostly connection that makes it seem like our policy is a huge success, when really, it's the phantom pulling all the strings. The bottom line is, our trusted model gets totally duped.
So how in the world do you catch a ghost? Well, researchers came up with a new tool, a new way of looking at the data that's designed to see right through the phantom's tricks and find the real story. And this is the solution. Instead of that standard method that gets fooled, they developed a new approach called an estimating equation. The old way is vulnerable to phantoms and the paradox, but this new way, it's specifically built to be robust, to ignore the phantom's noise and give us the true, unbiased causal effect.
Okay, so this all sounds fantastic in theory, but does it actually work? Well, the researchers didn't just stop there. They put this new tool to the test, first in a controlled simulation, and then on the messy, complicated data from the actual pandemic.
First up, the simulation. This is where they created a scenario where they actually knew the right answer from the start. The standard method? It was way off. That's the phantom bias in action. But the new method? Bam! It hit the bullseye, nailing the true causal effect perfectly.
All right, but a simulation is one thing. What about the real world? For the ultimate test, the team applied both methods to the real mobility and COVID-19 death data from 30 U.S. states. It really doesn't get more real-world than that.
And the results were pretty stunning.
In 24 of the 30 states they looked at, the new, smarter method found that the effect of reducing mobility was actually lower than what the old models said. So what does that mean? Well, it strongly suggests that our standard models were probably overestimating the impact of mobility rules, all because of those hidden phantoms.
So, after all this statistical detective work, let's just zoom out for a second. What's the big takeaway? Why does any of this really, truly matter? Well, it's actually pretty simple. Better models lead to better policy. This is not just some academic game. When we can filter out the statistical noise and see what's really going on, we can make much smarter decisions about which policies truly save lives and which ones don't.
And all of this leaves us with one last kind of chilling question to think about. This whole investigation uncovered a phantom in one of the most important data sets in recent history. It really makes you wonder, what other facts that we all just accept might just be phantoms hiding in plain sight inside our models?